This is part 4 of matrix operations. So this operator now that we have in this part is called the adjoint, and is a neat operator because it involves basically 2 in 1, 2 for the price of 1. It's very much in the spirit of transposition, but instead of using the symbol for transposition alone, here this is denoted with a star. Okay, but it involves taking the transpose of a matrix and also taking the conjugate. So it involves transpose and it involves a complex conjugate of the entries of the matrix, right? Conjugation and transposition. So it inherits a lot of the properties of the transpose of a matrix and also properties of complex conjugation. So the adjoint of the sum is the sum of adjoints. Concerning scalar multiplication, the adjoint of the scalar multiplication is going to be, this is not that difficult to prove, right? So if we're looking at alpha A and we're considering this operator, the adjoint, this is no other thing than transpose and the complex conjugate of alpha A. We can hold the transpose and take the conjugate, so this will be alpha A transpose. And now by taking the conjugate of this is alpha conjugate and the conjugate of A transpose, which becomes alpha conjugate and A star being this new operator. So this would be the so-called proof of this theorem. Is 1, 2, 3, 4, 5 steps. Basically, in almost in 4 steps, we could write a proof for this theorem. And again, as an implication of, remember how we had said, if you take the transpose of a matrix twice, transpose the matrix twice would give you the original matrix, and if you conjugate a matrix twice, that would also give you the original matrix. Well, both of these facts are used in the proof of the conjugate, the adjoint of a matrix is equal to the original matrix. So let's now consider an example of this operator, the adjoint of a matrix. Let's say we have this matrix with 2 rows and 3 columns, and we're going to compute the adjoint of this matrix. To do so, we're going to have to take the transpose, and we're going to have to take the complex conjugation, the conjugate of this matrix. So let's say, for example, that we first take the conjugate of this matrix. That means we're going to go on every row. In row 1, we have a complex number with 0 imaginary part, so the conjugate stays the same. The next number in row 1 stays also the same. The third number is going to have a complex conjugate as 3 plus 1i, right? So this would be the conjugate, the complex conjugates of the numbers on row 1 of the matrix A. And now by taking the conjugates of numbers in the second row, we have 4 and 5 plus 2i and 6, right? So this would be considered the conjugate matrix, the conjugate of A, okay, as a matrix operator. And if we now take the transpose, okay, here's the conjugate. We take the transpose of A conjugate. This matrix has 2 rows and 3 columns. The transpose of A conjugate is going to have now 3 rows and 2 columns. And this matrix would have as columns each of the rows, right? Or so, well, we could say that in a different way, but so here is the first row of this matrix, and those numbers in the first row are going to be stacked here as the numbers on the first column of the transpose of the conjugate, and then the numbers on the second row are going to be stored in the second column. So here we have 5 plus 2i, and then we have number 6. So this matrix is a matrix that has 3 rows, 2 columns, and this would be precisely what we call the adjoint of the matrix A.